our solutions in Python, so it will be in English, so everyone is welcome. So welcome him to the stage, and yeah, stage is yours.
Yeah. So hi, I'm Sławek, and I will tell you how to build a synchronous worker in Python, how to connect those both worlds, world of Python and asynchronous programming, and how to leverage 3 CPU cycles we can get from it. So first, few words about me. So as Janusz mentioned, I'm Sławek, and I'm a Python developer for more than 5 years. And after hours, I'm building this site called NaLunch.com. So if you are hungry and you want to have like well-priced lunches nearby you, you may visit. We started tests in Krakow, and we'll have some tests in Warsaw too. So if you enjoy eating well-priced lunch, maybe I will be more than happy to help you with this. Besides that, I'm studying on Jagiellonian University in Krakow, some stuff related to machine learning currently. All right, and this is the map of the knowledge, so yeah, you can check it out. All right, so let's get back to asynchronous programming. Here's our agenda for today, and we'll start about some backgrounds. Why do we process tasks? In background actually. Then I will go into jump into asynchronous programming, how it can help us there. Then we'll have a quick demo, and we'll see actually if it helps us or not. And then I'll suggest my own implementation of asynchronous worker. It's a simplified version, not expected to work like very well in production, but like showing you some kind of concept, how can it be done, and maybe it's not as difficult as you may imagine. So let's get started. All of it starts with a simple scenario where we have client and the server, and clients want to send requests to the server, and server sometimes responds and sometimes not. And even if it's the most simple scenario we can imagine, there are some assumptions. We assume that the server will respond quite quickly, and like in a matter of milliseconds or maybe a few seconds, like it's the worst case. And we don't want to wait long for the response. And this little assumption creates a lot of problems, because with this architecture we cannot go further, right? Because why? Why cannot we go further? Because there are some problems. There are some problems that clients can ask server many of things, like heavy, long-running computations, which will consume all of our resources on the server. It can query external services, which may time out, and our server won't respond at all. Also, we can have periodic tasks, which are running in periodic manner, and they're initiated outside of HTTP context. In HTTP, client initiates the request, and in periodic tasks, we can't do this, right? Besides that, we can have like tasks, like requests that take huge amount of resources, meaning we can make our service unavailable because it will consume all of our RAM memory, for example, and our server will become unresponsive at all. So we can see that this simple architecture has problems. And how do we usually solve these problems in like industry? So we make the whole architecture more scalable. Besides the server, we add this additional layer, layer of workers, and there is some broker behind the server. And the broker is just a terminology here. It's just a queue where we store tasks, which are picked up by workers. So just to go through this architecture, in here, client sends the request to the server. Server, let's say that it's really computationally expensive request. And server says, all right, I'll handle it later. I'll just send it to delegate it to the workers, which are separate processes, and I will just respond to the client. All right, so the task is delegated, it sits in the broker, and then when the time is right, when there are no other tasks, some worker may come in and say, all right, I'll process the task. And this is the part where we'll focus today. We'll focus on those workers. And in this architecture, you can see that there are many workers, because we can scale them like horizontally. If we have huge traffic, meaning more like lots of tasks in the broker, we want to process them quickly. And like many of those workers may consume more tasks, so our architecture scales in horizontal manner. And as we are on Python path, I want to give you some technological context to this architecture. So when it comes to the server, there is probably some kind of web application that is usually running on Django. There's usually some proxy server like in the front, usually it's Nginx. Then we have WSGI server like the Unicorn. And the most popular choice for the broker, meaning the queue in the Python world, is RabbitMQ. Sometimes it's Redis. But usually it's RabbitMQ because RabbitMQ handles additional stuff that is useful in the queues, like, for example, acknowledging tasks, broadcasting, and meaning routing tasks, and things like that. But Redis is just a simple key value store, but it's often used as a queue too. And then we've got the workers. And workers in this diagram are marked with like Celery. And Celery is the most popular library in Python for processing background tasks, basically. So Celery is maybe not thin, but it's an abstraction that gives you you don't know to which broker you're sending the tasks because Celery hides it behind you. You don't know if it's Rabbit or Redis, and it's really easy to create consumer's code. And by consumer, I mean the code that is running on the worker, in the worker process. So Celery provides those worker processes where the consumer's code is running. And in Celery, it's just a simple decorator in Python, like app.task. And here we go, we've got your consumer code. And Celery is also, please note that Celery is also in the server side because you want to send tasks to the broker, and then, so you're using Celery to do that, and then you're processing those tasks on workers, and also here the Celery goes to, it's used here too. Sometimes we use Redis queue as a simpler library, like less dependencies. All right, and if we have this architecture, we can say, all right, so now we can scale. We are having more users. Our business is growing. Our application is getting more momentum, and we are happy. Client is happy. Everyone is happy, right? It's scaling well. Unfortunately, in our project, it's based on a real-world example. In our project, something weird happens because it didn't work out. This is the feedback we had from the users. For example, there's some in Polish, some in English. So yeah, because it's the reality, right? Let's imagine the application that is syncing some products, right? And one really important user said, hey, my products are not syncing. And the DevOps messaged me on the Slack, Rabbit's memory is full, could you have a look? And we have a look at the architecture. The Rabbit is the broker. So meaning we have so many tasks in the queue. And also there's this pingdom alert that suddenly occurred on Slack saying, hey, Rabbit queue's length is down. Meaning there are so many tasks in the Rabbit, on the queues, that we cannot handle them anymore by reducing their number. So rational choice in the situation, decision in the situation is to actually add more workers because this is what our architecture is supposed to do. It is supposed to scale. So we proposed it, we were adding more workers, and finally it turned out that we cannot add more workers. Why? Because our resources, in terms of financial resources, are not enough. We found ourselves in this weird point, our application and the business, where our user base was growing, but our financial resources were not growing as fast as the user base. So suddenly we cannot add more servers, we cannot add more workers, we cannot add more processes, and the tasks are growing. So what do? We had to answer that question. And we started digging in, and we find out this problem in our project. And the title may seem a little bit scary because there's like shared critical sections. What does it mean really? But let me explain it to you because it's a really simple concept. So first of all, the critical section. Critical section is a term from concurrency field, if you remember from the college or somewhere, where there's the section of code that is supposed to run on maybe one process at the same time or like several processes. Let's say that's like limited number of processes at the same time. So what do we have? What do we have here? We have a task, which is our queue from the previous diagram. And we have several workers that are processing those tasks. And let's imagine that our workers are asking third-party service for something. Like let's say we are fetching some products, for example. And we cannot like ask this third-party service for like thousands of requests per second because they need to handle those requests. So what usually third-party services do is some kind of throttling. They're adding some limits that we are supposed to like adjust our application to, and at this moment we cannot send as many requests as we want. So workers, let's imagine there's thousands of workers and they are all asking this third-party service something. So now we need to adjust our code base. So what do? We make only limited number of workers. Like they need to have some kind of resource that they acquire, right? They have some kind of lock, and we make them we allow only limited number of workers to request that service. And this is marked in the diagram as a green box. I cannot see if you see the colors, but the first one is actually green. The following ones are yellow, and the green one is like allowed to do the requests, and the yellow one are not. And what's the consequence of that situation? It means that if we have like many tasks, our one worker is actually doing the requests, and all other workers are waiting for the lock to acquire this lock. So all of our workers are sleeping besides this one. And it's not the situation we want, because those other workers could have been processing some other tasks at the same time. Tasks that do not have the same critical section that this worker is actually processing at this time. So we found, all right, our workers are pretty sleepy, so we need to dig in further. How can we improve that? Oh yeah, and we also looked up some metrics, and it seemed that, hey, our RAM is used in 90%, our CPU is basically sleeping. Its usage was like maybe 10% or so. Alright, so we started digging more. Let's zoom in, let's see what kind of tasks are we having on our queues. And this diagram shows you some, maybe generic, I don't know if, maybe, probably not, you don't have all systems like that, but some of you may have. And let's follow through this flow. The arrow shows which direction time is, and usually the task starts with the serialization. We get some JSON, some information from the queue, and we deserialize it. We get some, let's say, product ID. We get some ID, so we can ask database for this product. Then we need to prepare our requests. Once we've done that, we can request the third party for the products, let's say, to actually update the information. So we need to wait for the lock. Then we requested the third-party service respond, and we've got our response. We deserialize it and save it to database. And it's a pretty common scenario. And what can we learn from it? We can learn that the yellow blocks are the blocks that are mostly waiting, waiting for something, waiting for input-output, waiting for the database, waiting for the lock, waiting for the third-party service, and again, waiting for the database. And the green blocks are the blocks where our processor is actually doing something. It's deserializing, it's preparing the request, and deserializing again. So we found that besides that our workers were sleeping at most, our tasks were sleeping too. So we thought that we had a problem. And as we are in Python world, what do? We import something. So we've imported asyncio, as it advertises itself as a input-output library, like synchronous. It's pretty sexy and cool and stuff. So we imported it, and then we suggested some solution, and we'll see results later. But first, maybe some quiz for you. I don't know if you can see it well. Probably, maybe some of you. So let's say that we've got two sections of code. One is asynchronous and one is synchronous. And they are printing some stuff to the output. And there's they are printing 4 numbers, 1, 2, 3, 4. And we are running the first task and then running the second task. On the right side, we are also running the first task and the second task, but it's some other manner. And the question to you is, do you know what will be the answer for the left section and the right section?
On the right, 1, 3, then awaits, then 2 and 4, and on the left, 1, awaits, 2, 3, awaits, and 4.
All right. So once again, for the left one.
The left one. The 1, 2, 3, 4.
All right, that's correct.
And for the right one,
yeah.
1, 3,
yeah.
something, and 2, 4.
Is it the only correct answer?
No.
Yeah. What's the second one?
Same as for the first one.
4, 2.
All right. So for this right column, it will be 1, 3, and then it depends.
Yeah.
Yeah, do you agree? It may be 2 or 4 or 4 or 2. It depends on the time of the requests on the network. Do you?
On the wait.
Yeah, exactly. So it's just to confirm that we all are on the same page in terms of asynchronous programming. It's not that obvious at first sight. So yeah, the answer is it may be 1, 3, 2, 4 or 1, 3, 4, 2. Right? Okay, we all agree? Yeah, I see. All right, cool. So once we know what asynchronous programming is, we can look up the ready-to-go solutions that we, as always, we don't have to strive for our own libraries. We are not in JavaScript world, right? So we can find out that there's IO tasks library. It's not so popular. So maybe we can find something else. We've got Pulsar Q, it's also not so popular. And wait, we've got Celery. Celery 5.0 is aiming to actually provide asynchronous workers. And we all know Celery, so it will be great. And the release was for March, unfortunately September, because the release is delayed. Yeah, I was looking at this date because, my presentation could be less relevant right now. Because we already have April, but they moved the release to the September, so we can wait for Celery. Once it's ready for production, we may just use it, and we may leverage our asynchronous programming in Python, for free, without implementing our own workers. Yeah, but we're here and we want to think about our custom solution. So why do we want to do that? It may be simple, because it's not that hard. It has some tricks there. It's not the same as synchronous, but once you get that, it's quite easy to implement. It's not that hard. You've got minimal dependencies. It's sometimes important in projects to have the less dependencies, the better. And you may have better fit for the problem. You may imagine that we had this problem with short critical sections, so you may come up with a solution alright, so we may have different queue for each task, and yes, you may do that, it will solve your problem, but then you may have short critical sections per user, so you don't have to have dynamic queues. You can make this problem more complex, and if your problem is complex, you can fit to this problem better, so you don't use external tools and make the problem fit to those tools, but you actually make the tools fit to the problem. But of course, there's no free lunch. There's no free lunch theorem. You can Google it. You can make a mistake, and you are responsible for maintenance. So yeah, it's always a trade-off. All right, I got some demo prepared. All right, you can take a photo so you can check out the code. Also after presentation, like this is the worker we're gonna be writing. I mean, it's already written, so I'll just show a couple of code sections. It's hard to like show it to you in this amount of time, but we'll have short demo. And the purpose of demo, yeah, all right, everybody take a photo, yeah. Yeah, and the purpose of demo is to show that actually the one system process can still handle lots of tasks compared to the synchronous code. So let's say I've got here the memory worker. All tasks are stored in memory. We don't use any Redis or Rabbit here. And what I'm doing here is basically running 1,000 tasks, which are basically sleep operations. We are basically sleeping for like 2, 3, like on average 3 seconds. And the purpose of sleeping is because we are simulating some requests to the third party. And let's say that we have synchronous code. So each task is sleeping on average 3 seconds. We've got 1,000 tasks, so it will run for 3,000 seconds. And it's about 50 minutes. Now here is a synchronous version. I'm adding some concurrency there, so to limit number of tasks we are having in memory right now. And let's see if we will wait 50 minutes or it will be quicker. It's just for like realizing, making you aware that asynchronous code is super fast. Like you don't have to believe me, but the process is already done. Like we processed all 1,000 tasks, which were basically sleeping. And you know asynchronous programming, so you know what happened. Like those tasks were like scheduled one after another. They were alternating like between each other. So it's probably worth like being interested in this technology, right? Yeah, cool. So this was like the quick demo. And now we want to make the first steps into introducing this asynchronous worker. So first we need to answer, can asynchronous, like asyncio help me? So we need to answer the question, is your task that you want to make asynchronous IO bound, meaning it's input-output related task, meaning are you asking some network stuff, are you asking file system, do you wait for something, do you wait for log, etc. The second question is, are there solutions libraries that already solve the problem, and are they asynchronous? And it's crucial for the Python world to have those tasks, to have those libraries asynchronous, because in Python, like comparing, for example, to Node.js, where all libraries are asynchronous from the ground, in Python, libraries are usually synchronous, and when you put synchronous library that is consuming like some amount of time in the asynchronous event loop, you are blocking the loop, meaning that the whole process stops running, meaning your tasks are not processed. So in Python, as the asynchronous world, asyncio especially, was added like from like Python 3.5 or so, it's like added, it's not from scratch, like from the Python beginnings. You need to take care of that. And also ask yourself about rewriting consumer's code to Python 3.7, or maybe if you're in Python 2, see if Twisted may help you. This is the library like before the asyncio, similar one. All right, so yeah, you're talking about Python 3.5. We're still in 2.x. Like, let's face the reality. It's not that wonderful. So my suggestions to you would be hide the logic behind the API. So hide the synchronous code behind some, I don't know, microservice, some API that is running in Python 2, and your worker is just asking the service over the network. It will help your worker not being stuck. Also, there's this trick called running executor. It will make your code, your synchronous code, run in separate thread, and your asynchronous code will await the result of the thread and get out of the result without blocking the event loop. So it is the case too. It may help you. So these are the hints for Python 2. And also, if you're in Python 2, just keep in mind that like in 8 months you may have some problem. Yeah. All right, so let's get into the architecture of our worker. This is my own implementation, so you might do it differently, but this is like the most simple. Like I tried to have those abstractions separated. So on the left, we start from the broker. The broker is basically the queue. So we abstract it with some class queue that has methods for getting tasks from the broker. Then we have queue processor, and there happens all the magic happens there. Basically, you're getting the task from the queue. You are deserializing this task and sending it to the customer, the consumer, and the consumer basically executes the code, meaning like fetch the products, like your business is doing your business logic. So this is like the most simple, like maybe not the most, but this is the architecture we'll discuss right now. And the basic mechanism for the worker is there are two states basically. There is one state where we fetch tasks from the queue, from the broker, to the limit. To the limit, I mean the memory limit. Because you need to be aware that when we are in a synchronous world, we can fetch from the queue as many tasks as we want. Because we are like, all right, fetch the task, and now do something with it, like ask some server, and now I can fetch another task. And again, ask some server, fetch another task, etc. In synchronous world, you would fetch the task, now you need to process it, so the process is sleeping, and now you can fetch another task. So in the synchronous world, you're naturally limited to one task, and in a synchronous world, you need to limit yourself. Because if you don't, you'll run over the limits and your memory will cry. So one state of the worker is fetch tasks to the limit, and another state is wait for completion of at least one task. And this may not seem intuitive at first, but what we're doing here is basically fetching to the limits, like those tasks are processing concurrently inside the memory, like inside the process. Then if we are full, we are waiting for those tasks which are still processing concurrently for at least one to complete. So then we can again fetch that one task from the queue to make our processing memory full. And these arrows to execution state are basically this is what we're doing here. We are basically alternating between fetching tasks, executing, fetching tasks, executing, waiting for completion, executing, and etc. We need to keep in mind that we are in a synchronous world and everything here is concurrent. So yeah, for example, fetching tasks alternates with processing those tasks. And we can see this on the diagram here. If we are fetching the first task from the queue, we're getting the first task, we are again sending the request for the second task, and then we can immediately send the request to some external service for processing the first task, right? But we haven't received our second task yet. Once we receive the second task, we can process the third task, we can ask for the third task, and again, in between getting tasks and asking for the next one, we can process those tasks we already have in memory. So we can see that the worker is like alternating between fetching, getting, then processing them, doing some stuff, sending some requests, saving to database, etc. And then again, fetching, getting, etc. Like, is it clear? Like, do you get the idea? All right, yeah. You can get back to it later also. I recommend to have some time with this code. Yeah, now we have code time, so we'll look into the implementation. Like, I don't know, how much time do we have? All right, so we've got like 10 more minutes. All right, cool. Cool, so let's look at the queues I prepared for you today. I don't know if it's visible. Is it visible? Yeah. It is. Okay, cool. So this is the queue abstraction I've shown you on the previous slides, previous diagram. So this is pretty simple. We've got some simple interface for enqueuing tasks and they queued this task, and it's already implemented for the Redis. And as you can see, the implementation is like really simple. We're just like pushing, getting element from the list from Redis, and we've already implemented in this way our queue. So two simple methods, basically enqueuing, so pushing to Redis, and dequeuing, so getting, I meant popping from Redis, and then returning some internal job that we will then process in our, how did I call this? In our queue processor, right? Maybe queue processor is not the best name because like you need to avoid processors. But if you have suggestion for the name for this class, please let me know. I'll make a pull request. So once we have our process, like our queue, because we were here first, so we have our queue, then I'll go into consumer code, so the second end of this worker. Let me just zoom in, where we have, for example, random sleep consumer. And the consumer, again, has a really simple method called consume, where you just consume the message from the queue. And we're just simulating some requests to third-party service. So we're basically sleeping for like 2 plus something seconds. And please note the await here, because you don't want to have like the common sleep, Python sleep here, without the await, since it will block the event loop, because it will block the whole process. It's really important. So yeah, keep that in mind. All right, we've got consumer, we've got our queue. So now let's have some more complex code. And actually, this is the whole implementation. So yeah, it can fit on the whole screen if I zoom out. And we have our queue processor. And queue processor is like the class which connects those two. So it takes the queue, it takes some consumer, some serialization, so it takes some serializer, and it's doing the processing part. So here, in this code, this while loop is basically this diagram I showed you before, where you schedule pending jobs, so you schedule jobs until the limit, and then you wait for the first completed job from your tasks in memory. So this is what we're doing here. We are scheduling until the limit and taking the first one from the memory. And we're going like back and forth there. And this is our worker. So how do we schedule those tasks? We schedule them by running dequeue method from our queue. Also, of course, there are some implementation details, like we have to have a timeout because our queue may not respond at all. We need to, for example, use the asyncio create task. It is really implementation detail, but if you're using asyncio, you know that if you're awaiting some function, you will actually wait in the code for the completeness of complete execution of this function. So if we had like a while loop with await here, we would basically do synchronous code. We would basically wait for each processing of each task. But we want to basically have them all in memory doing concurrent processing. So we need to run asyncio.createTask. And createTask is basically delegating the task into the event loop in Python and making this task pending or processing or done depending on its state. And the processing task is just our task being passed to consumer. So we're basically passing this task to consumer, acknowledging it, because we want to acknowledge on the RabbitMQ that it's done, if it's done, of course. If it's not done because there was some exception, we want to reject this task. This is like the most simple scenario. Of course, in this code there are some things that I haven't described right now, because, like, for example, here we are assigning some ID to some tasks. Why we're doing this? And this is because we are, for example, we want to keep our memory in some limit. So we need to delete tasks that are already done. So we need to remember them, and we want to we want to be tracing those tasks. So there are a couple of implementation details that you will get once you like study this code. But for the implementation purposes, it should be like this. So does it look simple? Like, does it look simple? Did I convince you? Yeah, maybe. Yeah, all right. So it's not that hard. I thought that like writing a synchronous worker was like, wow, I need to have like 7 months of the whole team of developers to develop new Celery. But it turned out that it's not the case. And we've used similar code to this, adding some monitoring, adding some additional stuff you need for production. After that, you're ready to go with this, and it runs in production. And we eliminated like 60 synchronous workers that were running on our server with one asynchronous worker, and we actually find out that our bottleneck has been removed. So our queues are not loaded with tasks anymore, and yeah, it was really, really nice. So let's get back to the presentation. Because there are some catches. The code looks nice, but I've mentioned already some of them. You need to keep in mind several things if you're doing asynchronous work. Like maybe you're not writing the worker, but you have like asynchronous in your job on your daily basis. You need to keep a few things in mind. For example, you need to limit number of tasks in memory. I've already mentioned that, because you will go out of memory if you don't do that. You need to use asyncio create task if you want to have many tasks in memory. If you're killing the worker, there may be already running some tasks, so you need to wait for the pending tasks. It's also worth keeping in mind when doing this kind of worker. Also, you should be using some kind of connection pools for the queries to database, for example. I haven't used it in the beginning, and there were some mixed like request response, like Postgres was really complaining about this. So after adding connection pools, it seems like, yeah, it's working well. But after adding connection pools, it seemed like that file descriptors are consumed in the system, and suddenly you need to ask your DevOps or someone to keep your limits of file descriptors in the system high enough to actually handle that worker in production. And the last catch, really important one, avoid blocking calls inside the event loop. It's the most important catch. For example, probably, how many of you use Redis in production? Or met Redis? Yeah, some of you. So Redis, as a key value store, is actually using event loop inside. It's implemented as asynchronous, it has asynchronous implementation. And I heard a story where Redis had so big objects inside the memory that actually getting those objects was quite time consuming. And as a result, because Redis is a asynchronous event loop, it was slowing down in terms of response on all kind of requests, because those long requests were blocking the event loop, and the Redis couldn't go. So the same event loop is here. Please keep in mind to actually not block it. And the summary. Asynchronous worker leverages 3 CPU cycles, and it's super fast. And if you have similar problems as I've described, it's worth to look at. It's well fitted for input-output with shared critical sections, because we had problem with shared critical sections, and our workers were sleeping. And now we've got one worker with, for example, 500 tasks in memory. Some are sleeping, some are not, but our worker is not. Is doing some job, is doing the job for the rest of those tasks. So it solves this problem for some cases. And also, and when we've got this worker running in production, it can actually turn out that we don't have to use that much memory, because when we have separate processes, each process takes some memory, and this worker is just one process, one system process, where you are leveraging the asynchronous code, so your cost is only the call of the function. Basically, those tasks are like calling the function. There was some site that this task, this asynchronous switching is the cost of 2 call functions, something like that. I don't know. I don't want to share wrong information with you, but something about it. And it's not that difficult to implement. So yeah, check out the workers code. If you're hungry, I'm happy to help you, and thank you for the for your time. Are there any questions?
Some questions. What about exception?
Exception?
Exception handling code synchronization. Because if everything is asynchronous,
Yeah.
it's possible to make conflicts in the data, and exception always is possible. It's
Yes.
Asynchronous.
Yes,
So you can.
so if you have exceptions, so I assume that those tasks are usually independent and operating on independent parts of data. So it's actually a little bit solves your problem, because if you have exception, this task is failed, you mark it in the database, for example, that it has failed, and you can then have some strategy for retrying it. It has also it wasn't implemented in this worker, but if you want to use it in production and have some kind of features that Celery has, like retrying tasks, etc., it would be like your responsibility to implement, like handling retrying stuff, and yeah. But if you're using the Rabbit, for example, as a broker, if there's exception, you can reject the task, and it will be requeued in the Rabbit. So then you can retry it, and yeah, there are many strategies to have for handling this. So it's a different task. Thank you.
What about database connection? Because you mentioned queries, but it is like quite difficult to handle like ORM database or ORM.
Yes,
ORM,
yes.
Asyncio.
Yes, that's true. So, for example, I couldn't find good ORM for asynchronous code in Python, because, as you mentioned, there's asyncpg, and it's for basically you're running raw SQL to your queries to your database. And if you want to do this, the tools for Python are not that mature, I think. If your queries are quite simple, you can go with asyncpg. It's super fast, and you can write like simple queries there. Like you can write any kind of queries, but you don't have advantages of ORM. Like Django right now is synchronous, so you can't use it. So my advice, if you have like code base in the Django ORM, you should encapsulate it in some microservice maybe, or something like that, and ask over HTTP to that microservice. It may help like migrating to asynchronous code. Like I couldn't find asynchronous ORM. Like there are some, but they are not doing this job well. I think so.
There is one asynchronous ORM.
Yeah.
It's very similar to Django ORM. It's basically
Okay.
and it's called Tortoise.
Tortoise.
Yes.
Yeah. Okay.
It's inspired by Django, but it's not yet production ready. It's 0.8.
Yeah.
version.
Exactly. Yeah.
It looks promising.
Yeah, there are a lot of promising, but it would be nice if we had like production ready and tested solution. Maybe if you tested it, you can share that it's ready to use.
We use Gino, is something like for the SQL.
Yeah.
It's asynchronous.
It works?
Yeah.
There are any problems? Yeah, it's perfect. So you've got recommendation. It's not mine.
What's the name?
Gino.
Okay, cool.
You had the first question about exceptions. You were saying as well that, for instance, if you want to kill a worker, you need to wait until the
Yes.
data has finished. What happens if the data returns?
Yeah, so basically you're just cutting all your connections, and there's like broken connection, and TCP packets are all around the place, and like if you have some process that depends on, for example, some transaction that is just running at the same time, you may have some state in your application that is not good later for handling. So yeah, so it's good to wait. So yeah, because you're killing often, like pretty often, so it's good to handle and wait for those tasks to finish usually. Yeah, this is the case.
Have you researched any servers, asynchronous servers for Python?
You mean the web application servers? Yeah, there are some. I can't tell right now.
Any of HTTP?
Yes, but HTTP is actually similar library to requests, where you just do HTTP queries. But you mean the server for handling requests from the clients? There are some applications. I think if you Google it, you can find immediately. I can't get names right now. If the audience.
There's Sunny.
Sonic, yes, Sonic, exactly.
Is it compatible with asyncio because it's based on?
Yeah, yes. Yes, it's based on internet. Yeah, Sonic was based. Cool. Are there any questions? All right, so thank you again.
Let me remind once again, please rate the speaker in the inventory.